Okay, go on now with the theory of solutions, going beyond regular solution theory. Okay. You remember when we dealt with RST is regular solution theory. You had the Gibbs energy of mixing was equal to the ideal term, RT XA log XA plus XB log XB plus your GXS term. And the GXS term would be heat of mixing plus the heat of mixing minus T times the excess entropy mixing, those two terms together being the excess Gibbs energy. Okay, in regular solution theory, then we used a quadratic expression for the heat and the entropy of mixing. So we had delta G was the ideal term, RT XA log XC plus XB log XB, plus, and then remember the heat of mixing was given by a term which I called omega x1 x2 minus eta T x1 x2 if you like, where omega and eta then were temperature and composition independent parameters. Okay, so this was the omega and eta temperature and composition independent parameters. That's your regular solution theory. Okay, now what we're going to do then, that only of course gives you two parameters, two adjustable parameters if you're trying to do curve fitting. If you've measured the excess Gibbs energy or measured delta G, you've only got your two parameters, omega and eta. So what we try to do is, I mean this of course then is a symmetric parabola, symmetric around 50%. You don't have a lot of freedom here. So in order to do curve fitting, when we're doing optimizations, we tend to then expand omega and eta. This is your standard polynomial model used by all sorts of groups, are expanded as polynomial expansions in the mole fractions. So actually here I've used, in this paper, now we're back to page 90, I've used a slightly different expression. Instead of delta H, I've talked HXS, but you know the heat of mixing and the excess heat of mixing are the same thing because the ideal heat of mixing is 0. Okay, and now rather than, and omega then is the heat of mixing term. Now I've expanded that then as we do here. This is just a general polynomial expansion where the parameters H0, H1, H2, H3 are constant terms, independent in this case of temperature and composition. Now if you have only one term, if we have only the first term, all these other terms are 0, then it's the regular solution model. Okay. In which case, here I call it H0, over here it's omega, it's the same thing. Okay. And if you have only one term, first term here, then you have only the S0 term, which is the same as the eta term here. So only the first terms, you got regular solution theory. So this expansion is based on regular solution theory. We go on, we go to higher and higher order terms, and then you can optimize the H0, H1, H2 terms, you can optimize the S0, S1, S2 terms. Those are the parameters of your model. Empirical parameters, just to do the curve fit. Okay, once again here we generally assuming, I'm assuming here that the H and SXS are independent of temperature. That is that the delta CP of mixing is 0. But again, that the reasonable assumption on most of these high temperature things over reasonable composition ranges, but in general, of course, H and SXS are not temperature independent. You would have to take into account the delta CP as well if you really wanted to do things correctly. We'll go into that, I'll show that a little bit later. I don't want to get sidetracked. Okay, so now what are these? So what are the meaning? Can you attach physical significance to these terms? Okay, so let's, remember in the regular solution theory where we just had the one term, you can attach the significance to these terms as the differences in bond energies. So remember the heat of mixing was given as the, this first term was the heat of mixing was N naught Z over 2 times 2 epsilon AB minus epsilon AA minus epsilon BB times x1, x2. That was your enthalpy term, as you recall. when you're doing a regular solution theory, this was omega. Avogadro's number, constant coordination number, and these were the energies of the pair bonds, AA, B, AB, AA, and BB bonds. Everybody remember that? You need a refresher? Okay, we just added up the number of bonds. Okay, this is in your notes, of course, somewhere. Where is it actually? Anybody know the section that that's at? Where did I do that? Yeah, section whatever, 5.5. If you want to look at equation 136 and 138. Okay. Equation 136. So I'll go to that. That's on page 49. All right, there we have it. So this was the heat of mixing of the first nearest neighbors. We worked this out just by counting the number of, this was in the 1 mole of solution, your number of AA bonds was XA squared in an ideal mixture, the number of BB bonds was XB squared, the probability of an AB bond was XAXB times 2, because it can be AB or BA. We subtract off the energy of the bonds in pure A and then XA moles of pure A and XB moles of pure B, combine terms, and we end up with this regular solution term. Okay, if you don't understand that, I'll go over it in more detail, because realizing what I did here. Okay, remember the assumption was you have a random mixture, which gives you the ideal mixing term. And in a random mixture, the probability of an AB bond is simply XA times XB. I mean XA times XA, the probability of a BB bond is XB times XB. Okay, we make the assumption that the Z, the number of coordination, the coordination number is constant with composition. And we're making the assumption that these bond energies are also constant with composition. And so that ends up then with this regular solution theory. Okay. We also did the same thing further down for the entropy term, the excess entropy term, in which we had exactly the same thing. The excess entropy term then was minus T times N naught Z over 2. And then we did the same thing where the sigma, these little sigmas, this was the entropy, the non-configurational entropy of an AB bond. This isn't configurational entropy. Configurational entropy is all up here, and we're assuming a random, configurational entropy is distributing in space. We're assuming a random distribution on the lattice sites. So this is your vibrational or electronic or whatever entropy associated with the bond. That's a little bit vaguer concept, but what the hell? Minus sigma BB. And again, you end up with an X1, X2. Okay, so that was your regular solution theory. Again, based on the idea that the Z is constant and that the vibrational entropies of a bond, A, have some sort of meaning, and B, that they're independent of temperature and composition. Okay, so that's how we arrived at that expression. And that was for the first nearest neighbor bonds, but you get exactly the same. You get exactly the same expression for the second nearest neighbor and the third nearest neighbor bonds. These are just the energies of second, third, fourth, fifth nearest neighbor bonds. That's the Z. So all the delta H, second nearest neighbor, third nearest neighbor, all look the same. They have different Zs and different epsilons, but it's the same functional form. So you end up finally with a term here that's just the C1 is the sum of the first nearest neighbor, second, third, fourth. It's still the same. Okay, so now we're going back to equation 168 where we're expanding this. So let us suppose that we're assuming now that the... Okay, let's change some of the assumptions then. Let's maintain the assumption that the mixture is still random. So the configurational entropy is still random mixing. A and B are randomly mixed on the lattice sites, so you still have the same ideal mixing term. But now let's assume, we can assume a couple of things. We can assume that these bond energies are not independent of composition, but they vary with composition. And a reasonable thing would be that they vary, to a first extent, they vary linearly with composition. In other words, the energy of an AA bond depends upon its surroundings. So you have an AA, here you have an AA bond. So here's two A atoms, here's an A atom, and this is the energy of the AA bond. But surrounding that are other atoms. Now this regular solution model assumes that the energy of this bond is independent of its surroundings. Okay, but in reality then if it's all surrounded by A's, it's going to have a different energy than if it's surrounded entirely by B's. And we can assume to a first approximation that it varies, say, linearly. In that case, the epsilon AB would be constant times x1 plus another constant times x2. I'm always mixing up A's and B's and 1's and 2's, AB. Okay, so we could assume that epsilon AB was some constant times XA plus another constant times XB or something like that. In which case, you could do the same thing for the energy of the AA and the BB bonds, and clearly what that's going to do is it ends up giving you a second term in those equations. Back on page, whatever, 90. Go back to page 90. All right, so clearly if each of these epsilons here, if each of these epsilons is a linear function of composition, a linear function of XA or XB, I think you can see if you rearrange the terms, you're going to end up with a second term. Okay? And that's called a subregular solution. And that could be now, what is the significance of these? I mean, it doesn't matter if you made this, if you made the epsilon AB linear or the epsilon AA linear or the epsilon BB linear with composition, you'd get the same, end up with the same functional form. You'd still end up with two coefficients. Or if all three were linear with composition, you still wouldn't have many more terms. You'd still have the same number of terms in your polynomial. Okay, so you really can't. And this could be applying to the first or the second or the third or whatever nearest neighbor. So to say exactly what H0, H1 are in terms of bond, which bond you're talking about, but I mean you're assuming that some of the bond energies vary linearly with some or more vary linearly with composition, you would get a second term. That seems to be a reasonable assumption. If you wanted to go one step further, they vary quadratically with composition, well then you're going to get a square term and so. So put it very simply, the variation of the energies, epsilon with composition, will give you a polynomial type equation. Similarly, the Z. Remember, this is the coordination number here. We're assuming the coordination number is constant, but the coordination number could change as you go from pure A to pure B. At least if you're in a liquid, it can if you're in a solid. It could if you're in a liquid, and that could also then give you a first approximation. Let's say Z varies linearly with composition. Well, then that's going to give you a second term here. If Z varies quadratically with composition, it's going to give you a third term. So to say exactly what these physically attached significance to certain bond energies to each of these terms is going too far because they're all the sum. Even if you have a regular solution, I mean, it's the sum of three, it's the difference of three different bond energies, just for the first nearest neighbor, so it's all mixed up. But the point is, it's reasonable to assume that you're going to have a polynomial thing. So if the bond energies or the coordination numbers vary with composition, the reasonable assumption is that you're going to get some sort of a linear expansion. Right? The further you get from regular solution behavior, the more terms you might want to add on to here. And it would be the same for these sigma terms. It's going to be exactly the same argument. The excess entropy term would also then give you a polynomial expansion. Okay, the most important point here is that this is still based on regular solution theory. We're assuming a ideal entropy term, this RTXA log XA plus XB log XB. Okay, this you can say, well, you'll have the idea, well, we're taking the regular solution, but we're just making a general polynomial expansion. So this is a very general expression for delta G. No, it isn't. That functional form, polynomial expansion, can be justified in terms of the regular solution theory if you're talking about an ideal. It's still based upon the regular solution theory. You're still assuming an ideal mixture. We're still assuming the probability of an AB bond is XAXB times 2. We're just assuming its energy varies with composition. Okay, if the system becomes the configurational entropy is no longer random, then the functional form is very different. Well, I gave a very simple example an hour ago. I took sodium chloride and I said you add potassium chloride to it, you get a limiting liquid of slope of 1. If you add 2 terms, you get a limiting liquid of slope of 2. If A were sodium chloride and B was potassium fluoride, you would immediately have to put a 2 in here. Okay, you got twice as many particles mixing. Okay, now this then gives you a second logarithmic term, which this goes to minus infinity when x approaches 0. So in the limit, as I said, in the limit, these terms, this term could not be fixed by this GXS term. If this was your sodium chloride, and you just put in a 1 particle slope for potassium chloride, and then you really have potassium fluoride over here, you're going to get a liquid as it goes like this. But if you don't put a 2 in here, no matter how many terms you add in your polynomial expansion, your liquid is going to come in to that 1 particle slope. Okay, because you just cannot express an xa log xa term in terms of a polynomial unless you have a huge infinite number of terms. Okay, so if you really have deviations from the configurational entropy is no longer roughly a random mixture, this is not the best way to represent your solution. You might, in the central composition regions, manage to fit the thing in reasonably, simply because you can fit up all sorts of things to polynomials, but certainly in the limiting composition regions, it's really impossible to fit, because you're not doing your configurational entropy right. And this is not the right functional form if the deviations from ideality are due to the configurational entropy. This is the right functional form, that is a polynomial, if the deviations are simply due to bond energies or whatever change, coordination numbers changing with composition. Similarly, if you have short range order, if you have here, you have pure A and pure B, but in the solution, say in the sense this is a liquid solution, at the central composition region, say 50% A, 50% B, you no longer have a random mixture of A and B, but the A and B's tend to prefer first nearest neighbor, so you have A, B, A, B. All A's are surrounded by B's, all B's are surrounded by A. You're going to get heats of mixing, and I'll show you later, and excess entropies of mixing, that again, you really cannot fit with this type of equation unless you put in a very large number of terms, and then everything's all screwed up. What you have to do is you've got to change your excess entropy. Your ideal entropy term has to be changed. So the polynomial expansion, the heat of excess heat and the excess entropy in the polynomial expansion are based, this polynomial expansion is based on the same chemical assumptions concerning the structure as regular solution theory, i.e., to a good approximation, the system is randomly mixed. Okay, and it's just the bond energies and bond entropies that change with composition. This excess entropy term here is a proper form for an excess vibrational entropy. It's not the proper form for an excess configurational entropy. And although you might be able to fit it some places in the composition region, you're certainly not going to be able to fit it elsewhere. And it's certainly not going to work if you then want to go from binary to ternary systems. Predict ternary's phase thermodynamic properties from binaries, because there you've got to be using the right. Whenever you extrapolate from binaries to ternaries, it has to be based on a proper physical model, not just a mathematical formalism. Okay, so that's what things mean. It does not. So the regular solution theory polynomial, and people unfortunately use polynomials when you have very large deviations from ideality. When you have small deviations from ideal mixing, then like in the regular solution theory, probably the ideal mixing term is probably pretty good. Unless, of course, you're talking about salts or something like the sodium chloride, potassium fluoride, then even if the thing's close to ideal, it's not good because you haven't taken account of what the actual dissociation is. But as the deviations from ideality get larger and larger, then it's less and less likely that it's going to be an ideal solution. It's going to be probably ordered. And in that case, this is not a good way to do it. And we'll talk about that later. Okay, anyway, but there's your polynomial model. Now, from the polynomial model for the integral hxs and sxs, you can derive these equations for the partial properties in terms of exactly the same coefficients. So the coefficients hi and si here are the coefficients h0, h1, h2 in the equations 168 and 169. Okay, this is just thermodynamics, and the way you derive equations 171 to these are the equations for the partial properties, are derived from these equations for the integral property. And of course it's based upon the tangent rule, if you have if this is HXS, if HXS looks like this, then this point here is HXS of B, and this point here is HXS of A at this composition. Okay, so if I have a polynomial expansion for HXS, I can obviously differentiate the thing and get a polynomial expansion for that. The equation you use is equation 92 on page 34. Equation 92 on page 34. And this equation applied to what I had was equation 92 there was for the G, so this was G. And here we have 1 and 2. And this point here is GX is G of, if this is G, then this is G of 2, which is the same thing as mu of 2. And this point here is G of 1, which is the same thing as mu of 1. And so, so at this particular point here, we'd have mu 2 is equal to G plus 1 minus x2 times dg dx2. Okay, so if you have an equation for G, you can get an equation for mu2. And this same thing applies for all the other properties, applies for excess properties, so you could replace in this expression here, this exactly the same thing. This could be G, well this is G1 and this is G2. If this is the XS1, well this is XS1 and this is XS2. If this is HXS, then this is HXS1 and this is HXS2. Okay, so you could have any property. F2 could be the set property of component 2. This is the corresponding interval property is 1 minus x2 times df dx2, where f is any integral property like h, s, xs, whatever, and f2 is the corresponding partial property. Okay, so for homework, convince yourself, is to derive equations 170 to 173 or whatever from the integral equations. Okay, so the integral equations, which were equations 168 and 169, from them derive the partial expressions on the next page. And this is the easiest. This is the easy expression to use. Any partial property or excess partial property of component 2 is equal to the corresponding integral property plus x1 times the derivative of the integral with respect to x2. So if you have f as a polynomial, as you do in equations 168 and 169, you can then calculate the partials as you have in equations 171 to 174. Okay, why do we do it this way? We use here, we expand it in terms of xb minus xa. Okay, remember xa is 1 minus xb, so you don't need both xa and xb. You could take this expression and in, say, expression, let's make it even easier, let's go back to 168. In expression 168, I've done the expansion in terms of xb minus xa. Why? That's called the Redlich-Kister way of doing things. But I can, of course, just, xa is equal to 1 minus xb. So I could write hxs is equal to xa xb, and here I would have h0 plus I would have h1 times xb plus h1 times 1 minus xb, okay, which would be xa. If I just take two terms, times h0 plus h1 plus xb, that's wrong, minus xa. right? Okay. Whatever. So anyway, I've taken XA, XB, and then I just add this, because this could be then XA, XB times A plus BXB or something. I mean, I can just rearrange it in terms of only XB. Okay, I could take the third term, and I could take XB minus XA, replace XA by 1 minus XB, expand that, collect terms, and I could end up then with HXS, and what I could end up with XA, XB. And rather than having a polynomial in terms of XB minus XA, I could write it as a polynomial. These are just other coefficients, A plus BXB plus CXB squared plus DXB cubed, and that is no different than that. I just rearranged it. Okay, replace XA by 1 minus XB and rearrange your terms, and you'll end up with a thing where these big capital A, B, C, and D are just some linear combinations of H0, H1, H2. Is that perfectly clear? Okay, so I call that this form up here is called the Redlich-Kister form. It's written down here somewhere. Here we go, Redlich-Kister form. Okay, the Redlich-Kister form is the XB minus XA form. The form I would have here, where you simply expand it as a polynomial in XB, I would call that a simple polynomial expansion. Okay. Or you could expand it in terms of XA, A plus BXA plus CXA squared, or some mixture of the two. Okay, there's any number of ways really you can rearrange your terms. Okay, and they're all equivalent. Okay, the Redlich-Kister, and the same number of terms. If you went up to the cubic term here, and then you rearrange it, that's the same thing as going to the cubic term here. And the H0, H1, H2, and H3 are linear related to the A, B, C, and D. One expansion is just the same as the other expansion. So why do we do it the Redlich-Kister way usually, rather than doing it this way? But well, why does everybody else do it the Redlich-Kister way? Why do we do it the Redlich-Kister way sometimes and this way sometimes? Because it would appear at first glance that there is no difference between them, but there is actually some difference. Oh, by the way, of course, if you only stop at one term, then of course this is the same as that. A regular solution doesn't matter. Okay, that's because, let's say we take HXS, and I'm going to write a XA, XB, and let's take it the simple polynomial in XB. I'm going to write that out again. So A plus BXB plus CXB squared plus DXB cubed, and so on. And let's say I'm trying to fit, I have experimental points here of HXS, and I'm trying to fit those points up to a curve. Okay, what's happening? Say I try to do a fit with one coefficient, which of course gives me a symmetrical curve, so I find it doesn't fit too well. I need two terms. I add two terms, fits a bit better. I add three terms, it fits a little bit better, and I go on, I find I need 4 or 5 terms to fit the thing properly. Okay, but now what happens when I go up to the high terms, plus EXB to the fourth, plus FXB to the fifth. This XB then is going here from 0 to 1. When XB equals to 1, this term is equal to XB to the fifth is equal to 1. When XB is equal to 0.1, that term is equal to 10 to the minus fifth. Okay, so this term here, this XB to the fifth term, looks like this. Very, very big over here, has virtually no effect over here. So therefore, adding this term can have an effect over here, but if I want it to have any effect over here to try to fit the curve better on this left-hand side, these coefficients, A, B, C, D, E, and F, are going to have to get bigger and bigger and bigger numerically. Orders of magnitude bigger as I add more and more terms. Otherwise, all I'm doing is fitting this end over here. Okay, so the F term, if this F coefficient has to be very large if it's going to have any effect over here. However, then it has a very, very much too big an effect on this side. So what you find if you do this, and you can try to do it sometime, take some heat mixing data, try to fit them up to a polynomial like this, and what you'll find is you fit it to one term. Let's say I fit it to one, A, B, C, D, E, F. And here I decide to fit it only to one term, so I put all these terms to be 0, and let's say my single term comes out to be, I don't know, 1,000 joules or whatever. Now I try to fit it to two terms. What I'm going to find is that the B term might be, 500, and this term now changes a lot. It goes down to minus 500. And then I try to fit to three terms. Now I'll find this will go to something 300. This might go down to 900, and this term here will go up to minus 10,000. and then I fit it to 4 terms, and these terms get bigger and bigger, and there's no correlation. The first term numerical value can be anything. It has doesn't remain constant at all. It's just a fit, because the functions, these functions are all correlated. And what you also find is, as you get to 4 and 5 terms, you generally find the signs going plus, minus, plus, minus, plus, minus. Your first term is positive, the second one's negative, the third one's positive, the fourth one's negative, and the reason is you've got to counteract it. If you want this f term to have any effect over here, where x is small, this term has to be very large, so it's way too big on this side, so the only way to get around that is to have this term negative to kind of counteract it on that side. Okay, so you find your terms getting bigger and bigger. You get up to, say, x to the 6th term, and remember now, this x to the 6th term has a value of 10 to the minus 5th at 0.1, which is still a reasonable composition. This is 10 to the minus 5th, so this term here has to at least be of the order of 10 to the 5th, 10 to the 6th, if it's going to have any effect. And you're trying to fit a heat of mixing that is maybe of the order of 1,000 joules, and you've got parameters that are like 10 to the 6th, 10 to the 7th. And you've got to maintain all the significant digits. You can't take a term that's equal to 10 to the 6th, 1.02. If you're trying to fit something to the nearest 10 joules, you have to go right out to all the terms. So what you find is the terms have no significance. Each individual term has no significance. The terms get larger and larger and larger. You get out to something like 7th term, you've got something like 12 or 13 significant figures, all of which must be stored in your data file. You can't truncate it. You have to store all those significant digits. Okay, and you can't really just. The other thing you can't do is, let's say I fit it to 3 terms, and I fit it to 1 term, then I fit it to 2 terms, then I fit it to 3 terms, and I say, well, the 3 terms doesn't give a much better fit than 2 terms, so let's go to 2 terms. I can't then simply take this and use these first 2 terms. That'll give me something totally stupid. I then have to actually go back, refit it with 2 terms. Is this kind of clear what's going on here? And this is because these base functions, xb, xb squared, xb cubed, are correlated. They're very strongly correlated. They all depend very much on composition, and they're correlated in that if you use 2 terms, 3 terms, 4 terms, the value. So this fit here may be very, very similar to this. Okay, with 3 terms, you get a very similar fit to 2 terms, but this isn't evident at all by looking at the coefficients, because the third coefficient is the biggest one numerically. Okay, and the first 2 coefficients have changed entirely from what they were before numerically, even though it's almost exactly the same fit. Okay, so this is because you got correlated terms. So if you're going to use a standard power series, you're going to find your terms getting bigger and bigger as you go over here, and you're going to find the signs alternating. You're going to find the terms, the actual numerical values don't remain constant, and you have to maintain large numbers of significant digits. Okay, because you're taking the difference. As I say, if f is equal to 1.02, that is 10 to the 6th times something, and e is 10 to the 6th times minus something else, it's the difference that's important over here, and therefore you've got to maintain it all the way out to 7 or 8 digits in order that it's accurate to 10 joules, because the coefficients themselves are equal to 10 million joules. All right, is it? So that's the problem with using straight power series. However, you can then, if you fitted this, and also just even curve fitting, with the computer, you've got to very quickly get into double precision calculations. You can't keep 8 significant digits, you've got to do 16s. You say, well, I'm only trying to fit, it's 1,000 joules, it's only accurate to 10 joules, I only need 3-figure accuracy. No, you don't. You need could need 16 or 20-figure accuracy if you go to enough term. Okay, so you got to do everything in high precision, and you get round off errors, and so there's your problem. Okay. So, even though once you had all these and you rearrange all these terms, you would end up with a polynomial that looks like that. So that's the reason we tend to use the Redlich Kister. And why is the Redlich Kister better? Well, because you look at these functions, xb minus xa, they don't. The functions xb, xb squared, xb cubed, xb fourth, xb fifth, all of these functions, if this is a and this is b, you have your constant, you have your first term, you have your quadratic term, your cubic term, your fourth term, your fifth term, your sixth term. They all go shooting up like this. But if I plot here a and b, and I plot my Redlich Kister terms, they're all, there's your constant Redlich Kister term, of course. The first term, which is xb minus xa, goes through 0 at 50%. The second term looks like this. The third term looks like this. The fourth term looks like this. They're all more or less symmetric around 50%, and they don't all have a maximum at one composition and a minimum at another composition. Okay, just draw up draw up these functions, xb minus xa, xb minus xa squared, and so on, and you will find that they look a little bit like sine functions. Constant, constant, one, actually, sorry, the quadratic term would look like that. The cubic term has 2 humps in it, the quadratic term has 4 humps in it, and so on. Okay, so it really is. The first term, this is your sort of your constant character, this is your linear character, this is your quadratic character, your cubic character. And what you'll find if you fit up to a Redlich-Kister polynomial, and you tend to use more, you do it with 1, well that's okay, let's try 2. 2 coefficients is better, 3 coefficients is better. Unlike the simple polynomial, it goes just the other way. As you add more and more terms, these coefficients tend to get smaller and smaller. Okay, because most thermodynamic properties don't have a x to the 5th sort of character, so they tend to get smaller and smaller. Okay, and then you can sort of see if you add another coefficient and that coefficient is really small, you've probably gone far enough. Okay. So you don't have to keep 16-figure accuracy, because these again, the functions don't get huge on one side and 0 on another, so you don't need extremely large values. So as a result, if you're trying to fit, say you're trying to fit a heat of mixing, which is the order of say 5 kilojoules, plus or minus 10, you only have to keep 4 or 5 figure accuracy, because all the coefficients are going to be of the order of 5 kilojoules, not 10 to the 7th or 10 to the 8th kilojoules. Okay, so the coefficients are all going to be of the same order as what you're fitting, so you can keep a low number of significant digits, makes it much easier to do the curve fitting, and in your data file you don't have to have huge numbers, but a lot of space. The coefficients tend to get smaller as you add more and more terms. They do not remain entirely constant. You can still not, say I fit it to 3 terms, I have H naught, H1, and H2, and I get 1,000, 500, 200. I say, well, I didn't need the third one, let's just truncate it. You can't quite do that. You then really do have to refit it to 2 terms, but the 2 terms aren't going to vary much from what they were. Okay, let's say you use 1 term, you got 1,000. You use 2 terms, you're going to get something like 900, 400. You use 3 terms, you might get 950, 300, 100, and then, okay, so you decide you don't need the 3rd term. You can't use that, but you can use this, but at least you see they're not changing very much. So this really is sort of the average value. This is your average first derivative, this is your average quadratic character, and so on. So it's a better way of doing it. You cannot truncate a Redlich-Kister. You can't just truncate it. You can't just say, oh, I don't need the last 3 terms, let's just use the first 2, because that won't be right. But it won't be that bad. You then have to refit it, but at least you can see what's happening by looking at it. So that's why we use Redlich-Kister. Most times. But remember, the 2 equations are exactly identical. You can take the Redlich-Kister terms and convert them into this, or vice versa. But if you were to take your Redlich-Kister terms and convert them into this, then you will find, just take a Redlich-Kister expansion of 7 terms and do this conversion, and you'll find that these terms here are getting bigger and bigger and bigger, and bigger, varying signs and so on. Why would you then ever want to use the regular power series? And you might want to use the regular power series when in fact this is the sort of form of the function you're trying to fit. And we'll show later, but when you're taking a system like CaOSiO2, in the CaOSiO2 phase diagram, or in many phase diagrams of silica with a basic oxide, you'll have some sort of things over here. Then over on this side, you tend to have a 2-liquid miscibility gap. Already showing you some of these things. If you go across the liquid phase here, you find the liquid phase over here remains more. Over here, you have kind of an ionic liquid consisting of calcium ions, oxygen ions, SiO4 ions, and it tends to be more or less well behaved in kind of subregular solution, 1 or 2 terms work. Over here you have a polymeric liquid with silicas all joined and broken bridges, a very complicated structure, which is a very different structure from here. And as you're going across here above the 2 liquid region, what we'll find is if we were to plot, say, the enthalpy of mixing divided by x1, x2, going across the liquid in such a system, we would versus composition, we would find it remains pretty much constant, and then goes up very, very steeply at the end, after about 80% or so. So in other words, this is very much something that is fitted with this type of function. Okay? It's something that remains more or less constant and then changes very rapidly over as you get to pure silica. That is then the form of the function you're trying to fit, and we find then actually you're better to fit it with this kind of expression. The reason being that if you use the Redlich-Kister terms, well, as I said here, in these terms, the big terms really have only an effect over here. So now you can add not two big terms here. They will have the effect you want over here, and they won't change this very much at all. And that's what you want. You don't want the terms that you're adding to try to fit this region to start to mess up the very simple linear relationship over on that side. If you start to use the Redlich-Kister, though, every term in the Redlich-Kister expansion basically has an effect over the whole composition range. So now I use one or two terms. I use, say, two terms, I get a nice fit here, but of course it's no good over here, so I start to add more terms in order to get this thing going up at the end, and now I find it starts to mess things up over here again. And I have a hell of a time trying to fit the thing. But if I use that, I get a much simpler fit. So there are some cases where if the function you're trying to fit goes up at the end, then you might want to use it. And we in fact do that in the slide database. In fact, Sage, and it makes a big difference and makes life an awful lot simpler. Okay, that's your Redlich-Kister. Questions? Okay, so I recommend that you try to derive equations 171 to 174 from this, and the main message here is that we're using Redlich-Kister because the terms are much less correlated, and this is mostly what you do. But the main message is that it's still based, the polynomial model is still based on regular solution theory. Your ideal mixing term is still, your configurational entropy is still the ideal term. Our x1 log x1 plus x2 log x2. And this model, the entropy terms here are appropriate for vibrational entropy deviating from ideal, but not for the configurational entropy if the deviation is significant, either due to having more than just one particle the solute dissociates, or due to ordering, long range, short range ordering. In that case, you've got to go to more sophisticated models that change the configurational entropy term as well as just the excess terms here. And even if you manage to fit your three binary around a ternary system, you manage to force fit your binary systems to a polynomial, and you get reasonable looking fits in your three binary systems. Okay, doing this, you're going into the ternary system from the binary, making an approximation, and when you're approximating a ternary system from a binary system, you are necessarily making a physical approximation. You're not just making a mathematical approximation. And if your physical assumptions are wrong, then probably your your prediction will be wrong. And if your equations are based upon random mixing, and it isn't randomly mixed, then you're not going to get a good approximation. Okay, so you've got to choose a model that reflects the reality of the solution. So we'll be going into this, of course, later in the term. But I'm pointing out things that people miss. Oh, this is just mathematics, but it isn't mathematics. It's a model. A model isn't just mathematics. A model is based upon some physical and chemical ideas. If you use the wrong model, you probably aren't going to get a good fit, and even if you somehow manage to force a good fit, you will not get good predictions if your model doesn't reflect reality. Okay, now I'm going to do something to confuse you a bit. You probably will not be doing this, but I give you some idea about a feeling for what's going on in the solutions. Let's go back to page 54. And this was figure on here, figure 22. Figure 22. Okay. I will refresh your memory about this. In this case, which was the silver-magnesium system, remember we had two phase diagrams down here. You have a limiting system magnesium solid solution, which is HCP, and you have a silver limiting solid solution, which is FCC. Okay, so there must be two separate Gibbs energy curves. They can't be the same curve because they're not the same composition. So I showed what we did is, so let's look at the curve for the HCP phase. The HCP phase is the phase that's stable from pure magnesium. Okay, so the HCP phase really only holds over this region. The rest of this curve up here is hypothetical. If you look at the phase diagram, the HCP phase is only stable to a few percent. Okay, but nevertheless, this is the curve we're going to use. So this is the Gibbs energy curve, goes from the chemical potential of pure magnesium in the HCP phase, mu naught here, and it goes up to a hypothetical chemical potential of silver in the magnesium HCP structure. Similar to the FCC, now this is a hypothetical Gibbs energy of silver in an HCP structure. This is the actual chemical potential of silver in the FCC structure. This phase here, I didn't finish it, but this curve here then would go up over here to a hypothetical mu naught of FCC magnesium. Mm-hmm. Now we can take the HCP phase and the so I'm talking about this curve here. So what I would say is the Gibbs energy of the HCP phase is X silver G naught silver FCC plus X magnesium, what's chemical potential, I guess. Chemical potential of magnesium HCP plus a constant Okay, so what I've done is I've referred it too fast. What if this curve here is assuming an ideal solution between these 2 points? Okay, so your Gibbs energy mixing is a Gibbs energy, an ideal Gibbs energy mixing, and it varies from X silver mu naught silver HCP to X magnesium mu naught magnesium HCP. But the way I've written it is I've written it with respect to that point, X silver mu silver is FCC, and then I've subtracted this term off again and added on this term, where C now is this would be this distance here. So this distance from here to here between the mu naught of silver and FCC and this hypothetical, this distance is C. I know here I called it RT log gamma naught, and it is in this particular case, but it's a constant. Is that clear what I've done? So, okay, it's gone from this term here, completely cancels out here. Sorry, SC times should be X magnesium. X silver times C. Oh, C is. Start all over again. There we go. That's it. Okay. Correct? Start again. Okay. The equation of this curve here is X silver, chemical potential of silver in HCP, plus X magnesium, chemical potential of magnesium in HCP, plus the ideal mixing term, and this term X silver magnesium FCC, X silver mu silver FCC is added here, and the same term comes off over here. Okay, so that's just an ideal mixing curve between this point and this point, but I've written this mu silver, where this distance here is this distance here. So not C, forget C. Okay, so this is a change in standard state, basically, if you like. So how do we explain this? We say it's an ideal mixture, so we say you've got random mixing. But remember what happens is if you started off over here in magnesium, and you start to add in silver, every time you add in a silver, it goes into the same environment of HCP. which has a certain energy connected with it, and every silver that you add has, because it's a dilute solution, every silver that you add gives you the same energy increment. So you end up with a term that's mole fraction of silver times a constant. And this is the energy difference you get. See, it's not an ideal solution because it's not the same. The silver does not find itself in an FCC environment, it finds itself in an HCP environment. This term, this difference here, is the difference between the energy of a silver in an HCP environment, in which it finds itself in the solution, and the energy of the silver in the FCC environment, which it was in when you pure silver. So you take a one atom of silver, which has this chemical potential, FCC, you put it into the HCP phase, and this is the difference in energy that appears, times the mole fraction of silver. Every time you add a silver, you get the same energy increment. Okay, so this is due to the fact that the silver, every silver goes into the same environment of being surrounded entirely by HCP magnesium, and every time you add a silver, this is the energy increment you get. The pure silver was in an FCC, it now dissolves and finds itself in an HCP environment, and this is the difference in energy, which is positive because the silver likes HCP, likes FCC, it doesn't like HCP. Okay, we went through the whole thing before. This is R2 log gamma. Okay, you remember? Now we say then, well then you can go a little bit further and you can say, well let's say then that the system is, okay, that's assuming then that's your ideal Henryan solution. And I said, well then you could add a term here, omega x magnesium x silver, if you wanted to make it a regular Henryan solution. Okay, so this is, again, just with respect to these standard states, you just added a GXS term, x1, x2 times GXS to that term. So this is just a regular solution term added on top of the... Okay, so remember the excess, why do we have this term? Well, this is simply because, why do we get this? Well, it's because every time you add a silver, in the limiting region as you add a silver, every silver goes in entirely surrounded by magnesium, but after a certain point, after the silver concentration gets high enough, a silver sees another silver, and that ends up giving you a quadratic thing, just like the regular solution theory. Okay, so this is a reasonable way then to fit up this type of a curve. That's the way we usually do it. Okay, everybody happy with that? Then, that's for the HCP phase. For the FCC phase, which would go up like this, I could do the same thing for the FCC phase. I could say the Gibbs energy of the FCC phase would be X silver times G naught silver, FCC, plus X magnesium, mu naught magnesium, HCP. I'm just doing the mirror image of what I did, plus now X magnesium times mu naught of magnesium, FCC, minus mu naught of magnesium, HCP, plus the delta G ideal, plus omega, if we call this omega 1, we'll have to call this omega 2, times the product of the x's. Okay, it's just the exact mirror image of what we did there, and this would apply to the limiting region over here with the solution silver with dilute solution of magnesium and silver. Anybody want me to go over this again, or are we all happy? So this is an appropriate equation for the HCP solution, which has a hexagonal structure. You have an hexagonal structure and you're throwing silver, which prefers an FCC structure, into an hexagonal environment. Okay, and every silver then has this sort of difference in energy, which makes it like this Henryan term. And you can also add on top of that a regular solution term to make things fit a little bit better. On the other side, it's exactly the same thing. I'm referring it to the two standard states here. I'm adding on the magnesium now in the hypothetical FCC and the HCP, an ideal term, and another. And this is appropriate then for an FCC solution into which I'm putting magnesium in relatively dilute quantities. And this is the modeling that we basically use. And just to finish, as I said before, this mu naught silver HCP should really depend upon the solvent. It will be different from HCP magnesium as HCP zinc, but we try to make a compromise so that we can just talk about this as the chemical potential of action of HCP. So I'm just repeating what I said in the previous lecture. All right, but now what do we do if the two limiting cases are, if the two limiting solutions have the same structure? Okay, so here we have, this was our HCP phase, and here is this FCC phase. And when they have limiting structures are different, then that's what we do. But let's say they have the same structure, then they can in principle join in the middle. That is, you can have one continuous phase across all compositions. And as I said, although we may be in the silver magnesium system, well, in a given system, you may not have the two limiting terminal solutions ever forming a complete solution, but as you go into a ternary or a quaternary system, they could very well. In which case you really can't do this. You really have to treat the thing as a single phase. You can't, even in theory, do this. You have to treat it as one solution. Okay? You look like I didn't tell you this before. Okay, we've been through that before. If these have the same, if this is FCC and if this is HCP and this is HCP, then you can't treat them as two independent phases, because then they would never come together at a high temperature. They would never come together. It's got to be one continuous solution. Okay? Or else, even in a binary system, you may have a binary system AB in which you have limiting solid solutions here. The alpha and beta, they have the same structure, alpha plus beta. They never, so you can treat this as one phase and you can treat this as another phase. But now if you go to a ternary system, A, B, C, you may find in the AC system, the alpha phase and the beta phase are, these two phases are completely miscible, and so your miscibility, your two liquid region, your two solid region in this ternary system actually ends here, and here you have, say, an FCC solution that's in all compositions. You can't have one equation for this phase and one equation for this phase if somewhere in here they join up and form a single phase. Okay, you can't. If you have a system, even a binary system AB, and you have a miscibility gap here with two liquids, okay, and this system over here and over here, you could have different, you could have one equation of G for this solution here and one equation of G for this solution, but when you get up to this temperature, they've got to join up in the middle. Okay. So when the two systems have the same structure, which is of course always the case in a liquid, and in the case of a solid can be the case if they have the same crystal structure, then in principle we're not really supposed to fit them up this way with one equation here and another equation in the other phase, because then there's always a two-phase region. You can never at any temperature or composition ever get a single phase at all compositions. In that case, you should say the Gibbs energy of the phase would be XA times mu naught A plus XB times mu naught B plus delta G ideal plus omega x1, x2, or XA, XB, if you want to use a regular solution, or you could add other terms onto here. Okay, but you only have one equation for the entire system, for the entire phase at all compositions. Okay, is everybody happy with that? Because now I'm going to go on and show you what's the problem. This was just a review. Okay, however, this equation here now, if they're the same composite, if they're the same structure, this is always the case in a liquid, you now have fewer adjustable parameters here. When I did it before, I rubbed it off, but you had this equation here and you had this equation here. We had the term mu silver HCP minus mu silver FCC. That was one adjustable parameter, and your regular solution term omega was a second parameter. So basically we had two parameters for the HCP phase to fit it. We could fit this G naught here was an arbitrary parameter we could fit, and we could also fit the regular solution term. And for the FCC phase we had, again, two adjustable parameters, so we ended up having four adjustable parameters for the two phases, whereas here now we've treated the two phases as one phase and we've only got one adjustable parameter. Okay, so you have far fewer adjustable parameters, okay, than you did before. So you're certainly, if you're going to do it this way, you're not going to be able to fit it as well in the limiting regions unless you add a lot more terms. But okay, so you add a lot more terms and you fit the thing up okay. The point is though, you're never getting exactly the same composition dependence. You're not getting the same, this cannot be related exactly to what you had before in the two, but it's fairly close. Okay, the problem is, what happens is that we find that not many, but we find several solutions. Actually, what you're assuming here then is you're assuming an ideal mix. This is a regular solution, and even if you add the additional terms, as I say, you're assuming a regular solution with linear dependence of the parameters on composition. You're assuming you got the one structure over the whole region. You're assuming more or less constant, all the assumptions of regular solution theory apply. You're assuming kind of the same structure across the whole thing, but the structures can actually be fairly different. Even if you have a liquid, like I said, well, I gave the example before of, say, calcium oxide and silica. Here you have two liquids. Well, that's sort of an extreme case, but the liquid over here is ionic. The liquid over here is very different, and you don't expect the same sort of polynomial expansion to apply to the entire composition region. Even though you're trying up here, you're going to have to force yourself to do it. Okay, you're forcing yourself to have one expansion over the entire composition region. Whereas actually, over a region down here where you have a limiting region here and a limiting region here, each of these regions is much more easily fitted with the two expansions there. You can probably fit this region with two coefficients, as I said, and this region with two coefficients. But to try to fit the whole thing, and all compositions require many, many coefficients, and is much more difficult. Now, you can't get around it, you sort of have to do that. But nevertheless, you have many systems in which you have one terminal region which really does have one structure. You have another terminal region which really does have a very different structure, and there's only a region in between where the two structures join up. In other words, or let's say this is my one Gibbs energy term for the alpha phase, this is my Gibbs energy equation for the beta phase, and I said in the middle they have to join up, but you find that this equation here fits very nicely up to this region, and this other equation fits very nicely to this region, and only in the central region do you need to have the two come together somehow. So treating this as the dilute solution model, and treating this as the dilute solution model is pretty good in the terminal region, because that reflects more what's going on in the solution. The solution really does have two terminal regions with sort of very different structures, and a central region where the two structures sort of have to come together somehow. So fitting this region all up to 70% silica with one model, and fitting it up going the other way to from 100 to 80% silica with another model, give you a very simple fit here, and this model would give you a very simple fit over here. If you try to fit the entire, but you can of course join them together because they have different endpoints up here. If you then try to bring them together in the middle with one equation, then you end up with a much more complicated equation with far more terms and so on, because most of your time is being spent trying to fit that transition region. Now we have really no choice, and that's the way we do it with the one term. But I'm just going to show you a couple of, but just to understand how the solutions go, let me give you a, I should have done that. I have this. I thought in here we have this is kind of an extreme example. This comes from an experimental paper a long time ago. This is the phase diagram. This was in your notes there. Or what's that? Oh, number 7. This is your silver chloride, silver sulfide phase diagram, and here's another error. Should be Ag2S. And you can sort of see what happens here. It's a simple eutectic system. This is your mixture of silver chloride and silver sulfide. Silver chloride is an ionic salt, a lot like sodium chloride with silver ions and chlorine ions. Liquid silver sulfide has more or less silver ions and sulfur ions, but has a lot of free electrons. It's an electronic conductor. There's electronic bonding in the thing, sort of like a metal. And the structure is quite different from that of silver chloride. It's a very kind of different liquid. what you find is as you add silver sulfide to silver chloride, you can have a very simple model over on this side, and if you fit this model up, you can fit this up to that very simple regular solution type theory that I showed before. If I'm plotting here the GXS of silver chloride versus X squared silver sulfide, you get almost a straight line. Okay, remember that was the equations I put on the board for a curve like this. The G0 is the G0 plus the ideal plus the X1 and X2 times a regular solution term. Okay, and you're finding that that fits very, very nicely to the liquidus on one side, fits very nicely to an equation like that we used to fit this curve, up to almost up to the eutectic expression, up to the eutectic. On the other side, over this region over to here, you fit this up, and it can be fitted up very nicely to another polynomial, another expression, which just has the regular solution term plus this change of standard state term. Okay, so this system is fitted very nicely with these two expressions. Here you have a very simple regular solution model, but with respect to this other standard state. And over here you have a regular solution model right up to here. And we find there's only this small transition region in which sort of the two structures have to come together. If you fit up this entire region, you can fit it up very nicely to the two-parameter equation, the change of standard state plus the regular solution term. And over on this side, you can fit this side up very nicely all the way up to here to the two-parameter term with the G0 minus G0, one structure minus G0, the other structure plus a small regular solution term. And the regular solution terms are even reasonably small. Only if you try to fit the entire thing up over the whole region, then you have a hell of a time trying to fit it, because you've got to somehow get this region in the center. But what this shows you is that physically, and you have no choice if you want to put this in a database, you can't have one equation that fits up to here and another equation that fits up to here, and there's no way to put them together. Okay, but if you do it, you get one very simple equation here and a very simple equation here. And what this is telling you structurally is that all the way up to here, the structure of the liquid is very much an ionic silver chloride. You have silver chlorine ions, and the sulfur is going into the chlorine site somehow, but the structure is remaining more or less the same, and this is an ionic liquid. And it's telling you up here, this is basically the silver sulfide, and chlorine is going in there, but you're maintaining the silver sulfide structure. And physical properties too, you'll see this remains an ionic liquid up to here. Over here you have pretty much electronic conduction all the way to here, and then there's only a transition region where things are really weird. Okay, so physically, we'll just show you physically what's happening. You fit this up to these very simple equations. If you can fit something up to a very simple equation, it tells you that there's probably something reasonable about the model that led to that equation. So now we're not going to be doing this because we just don't do it that way for the reason I said, but this still shows you how, and it was some time ago, many years ago, Darkin talked about this, and he showed many examples, and of course calcium silica was a prime example. The same thing, you can fit up a two-parameter equation over here and a two-parameter equation over here. It's only when you try to fit the whole thing across that you need your 6 or 7 parameters, and it's a total pain. And we did this, actually, this is a paper I wrote, they measured, we did the same thing with thallium chloride, thallium sulfide is virtually the same thing. Thallium is just one below silver in the periodic table, you get virtually the same thing. So now this is a bit of an extreme case, but in many cases it still indicates that at one end of the solution you have one sort of structure, at the other end you have another sort of structure, and when we try to fit solutions with one equation, we kind of tend to lose this, so you're losing some physical reality in here by doing the one equation, although you really don't have too much choice. So this comes up to Darkin's formalism, and I think everybody's getting tired, so you might want to look at number 8. And in number 8, actually you don't have to read the whole paper by any means. You don't have to prepare this, you want to prepare. I want to talk about Darkin's formalism, and I'm going to talk about the Wagner's formalism, which is a bit more important because you still see that used a lot. So you might want to read page 1 of this. You don't need to read this. Equations 13 to 16 for the ternary, you don't have to look at that, and then read this up to. Well, read it up to the end of part A here. Read it up to this point. The unified interaction, so it's what page you're on. Yeah, the end of the first, to the end of the first paragraph on page 871, but you don't have to worry about equations in the ternary system there. Whatever there, I lost him again. Well, just skip the parts about the ternary system and just up to that point, but skip the ternary system. I'm thinking about the doctrine's formalism in terms of what I said. So Darkin a long time ago worked out this formalism and showed that it really did fit a lot of systems. And Wagner's formalism, I'll be talking about that too. And you might want to read about Wagner's formalism and why it's the problems with Wagner's formalism, because that's still used quite a bit. Okay, so anyway, the whole thing about this Darkin's formalism is that in many systems you get the, like that silver chloride, silver sulfide, you really do have two terminal regions in which the structure is more or less the same for a long way on one side and another structure on the other side with a transition zone. Fitting the thing to one equation, you lose that physical aspect of the thing, and you're saying that's sort of one continuous structure across the whole thing. We don't have too much choice, however, because, well, we don't have too much choice. Okay. Let's stop. Okay, I'll come back on Thursday. Thank you.